Radar doesn't see airplanes. It never has. It never will. What it sees are signals, echoes, tiny fragments of energy that return after hitting something in the sky. And from those fragments, it tries to reconstruct reality. It tries to decide whether something is there or not. And more importantly, whether that something matters. Now imagine you are sitting in front of that radar screen, watching a field of noise, random fluctuations, signals bouncing from the ground, from the air, from everything that surrounds you. And suddenly there is a return, but it is weak, unstable, inconsistent. It appears for a moment and then fades. Not strong enough to confirm, not clear enough to trust. And now you are forced to make a decision. Is it real or is it just noise? This is where the B2 lives. Not in invisibility, but in uncertainty. It does not try to disappear from physics. It simply refuses to become a clear answer. It turns itself into a question the radar cannot confidently solve. And when a system designed to detect threats begins to doubt its own data, it slows down, it hesitates, it second guesses, and that hesitation is the real vulnerability. So the real secret is not that Iran's radar cannot see the B-2. The real secret is that it may see something, but it cannot be sure, and in a system where certainty is required to act, uncertainty becomes the most powerful form of stealth. If you want to understand why something like the B-2 is so difficult to deal with, you have to start by removing a very common assumption. Radar is not a camera. It does not see shapes. It does not see outlines. It does not see a bomber flying through the sky. What it does is much simpler and at the same time much more limited. It sends out electromagnetic waves, and then it waits. Those waves travel outward at the speed of light, spreading into the sky, hitting everything in their path, the ground, clouds, birds, buildings. And if there is an aircraft, they hit that too. And when they hit something, a portion of that energy is reflected back, and that returning energy is all the radar ever receives. From that return, the system tries to reconstruct a picture, not a visual picture, but a mathematical one. Distance, speed, direction. Strength of signal, that is the entire world of radar. So when people say radar sees an aircraft, what they really mean is that radar detects a reflection that is strong enough, stable enough, and consistent enough over time to be classified as an object. There is no image, no silhouette, just a signal that stands out from everything else. And this is where things begin to get interesting, because the entire system depends on one fragile condition. The reflection has to come back. Now take a normal aircraft, something made of metal with vertical surfaces, edges, corners, and flat panels. When radar waves hit that kind of structure, they scatter in many directions, but a significant portion of the energy reflects directly back toward the radar source, especially from perpendicular surfaces. And that creates a strong return, a bright, clear signal that rises above the background noise. Easy to detect, easy to track, easy to lock onto. But this is not because the radar is powerful. It is because the aircraft is cooperating with the radar without realizing it. Its geometry allows energy to bounce back efficiently, almost like a mirror in certain orientations, and that is all radar really needs, a reliable echo. Now imagine changing that condition, not by making the aircraft disappear, but by changing how it interacts with those waves. Instead of reflecting energy back to the source, you redirect it, you scatter it away. You absorb part of it. You break the coherence of the return so that whatever comes back is no longer strong or stable. The radar still sends out waves. The aircraft is still there. The physics has not changed. But the outcome is completely different, because now, instead of receiving a clear signal, the radar receives something weak, something inconsistent, something that looks almost like everything else in the environment. And this is the key point. Radar does not ask, is there an aircraft? It asks, is this signal different enough from noise to matter? Noise is always present. Reflections from terrain, atmospheric disturbances, electronic interference. Even the radar system itself produces internal noise. And all of that creates a background, a constantly shifting field of meaningless signals. For an object to be detected, it has to rise above that field. It has to be distinguishable. It has to be recognized as something real. So detection is not about existence. It is about contrast. If you cannot create enough contrast between the object and the background, then from the radar's perspective, there is nothing there, even though physically there is. And this is where the entire idea of stealth begins. Not as invisibility, but as a manipulation of contrast. The goal is not to eliminate reflections entirely. That would be impossible. The goal is to reduce and distort them just enough that they no longer stand out. You are not removing the signal. You are burying it. Once you understand this, you start to see the limitation. Radar is not failing because it is weak. It is failing because it relies on a very specific condition. A clean, strong, interpretable return. If that condition is broken, even slightly, the system struggles, not because it cannot receive signals, but because it cannot confidently interpret them. So the first truth is simple. Radar does not see objects. It sees reflection. And if you can control the reflection, you control what the radar believes is real. If radar depends entirely on reflections, then the most direct way to defeat it is not to fight the radar itself, but to change what happens when those waves hit you. And this is where the first real trick of the bee begins. It does not try to block the radar. It does not try to overpower it. It simply refuses to send the energy back. When a radar wave strikes an object, the outcome depends on geometry, not intention. Surfaces, angles, edges, all determine where that energy goes. And in most aircraft, those surfaces are not designed with radar in mind. They are designed for aerodynamics. The structure, control, and as a result, many of those surfaces end up reflecting energy directly back to the source, creating a strong and clean return. The bee changes that relationship completely. Its shape is not just unusual, it is deliberate, a flying wing with no vertical tails. No sharp corners that face the radar directly. No simple flat surfaces that act like mirrors. Every curve, every angle is carefully chosen so that when a radar wave hits it, the energy is redirected away from the source, scattered into directions where the radar is not looking. Think of it like shining a flashlight at a mirror versus shining it at a rough wall. The mirror sends the light straight back to your eyes, bright and clear. The wall scatters the light in all directions, and what comes back to you is much weaker, much harder to distinguish. The B, too, is not a mirror. It is closer to that rough surface, but engineered with extreme precision so that the scattering is not random. It is controlled. And this control is the key, because even a small change in angle can dramatically change how much energy returns to the radar. If the surface is oriented just right, the reflection goes somewhere else entirely. And from the radar's perspective, it is as if the object absorbed the signal, even though in reality it simply redirected it. But shape alone is not enough, because some energy will always find its way back. Physics does not allow perfect redirection. And this is where the second layer comes in. Materials. The surface of the bee, too, is not just metal. It is coated with materials that absorb part of the incoming radar energy, converting it into heat instead of reflecting it. And while the amount absorbed in any single interaction may seem small, when combined with a geometric scattering, the total return becomes extremely weak. So now you have two effects working together. Less energy is being sent back, and what little remains is scattered and incoherent. And that combination is far more powerful than either effect alone, because radar does not just need energy. It needs structure. It needs a signal that is consistent enough to recognize the B. 2 removes both. It reduces the strength of the return and it disrupts its coherence, turning what could have been a clear signal into something fragmented, unstable, and difficult to interpret. And this is where the trick becomes more subtle, because the radar may still receive something, but that something no longer behaves like a typical aircraft reflection. It flickers, it shifts, it appears and disappears depending on angle, distance, and frequency. And that inconsistency makes it extremely difficult for the system to classify it as a real target, because radar systems are designed to filter out exactly this kind of behavior. They are trained to ignore signals that look like noise, that lack stability, that cannot be tracked reliably over time. So instead of trying to be invisible, the B2 takes advantage of the radar's own logic. It presents itself in a way that the system is likely to dismiss, not because the radar cannot detect energy, but because it cannot confidently label that energy as a threat. And this leads to an important realization. The B2 is not defeating radar by breaking physics. It is defeating radar by working within physics more intelligently, by understanding exactly how waves interact with surfaces and designing every aspect of the aircraft to control that interaction. It is a game of angles, materials, and energy flow. And the goal is not perfection. The goal is just enough reduction, just enough distortion to push the return below the threshold of certainty. Because once the reflection is no longer reliable, once it no longer points back clearly to the source, the radar loses its most important advantage. The ability to say with confidence, there is something here. And that loss of confidence is where stealth truly begins. Now, once you understand that radar depends on reflections, and that the B2 reduces and redirects those reflections, the story becomes more interesting. Because detection is not just about whether a signal exists. It is about whether that signal can stand out from everything else. And this is where the real battlefield is. Not in the sky, but inside the radar system itself, in the constant struggle between signal and noise, Every radar operates in a world that is already full. The ground reflects energy. The atmosphere scatters it. Weather systems distort it. Electronic systems interfere with it. And even the radar's own components generate internal noise, a continuous background of meaningless signals that never truly disappears. And this background is not small. It is always there, shifting, fluctuating, unpredictable. So when a radar sends out a pulse and receives something back, it does not automatically know what that something is. It has to decide whether the return is significant or just part of the noise. And this decision is based on thresholds. If the signal is strong enough, consistent enough, it is treated as real. If it falls below that threshold, it is ignored, filtered out, dismissed as irrelevant. This means something very important. An object can physically exist, reflect energy, and still not be detected. Not because the radar failed to receive the signal, but because the signal was not distinguishable enough from the background. It did not rise above the noise. And this is exactly where the bee, too, operates. It does not need to eliminate its signal completely. It only needs to reduce it to the point where it blends into that background, where the radar sees it as just another fluctuation, another meaningless variation in the sea of returns. Think about what that means from the perspective of the operator. You are looking at a system that constantly produces small signals, random spikes, temporary echoes, and most of them are nothing. They come and go. They have no pattern, no continuity, and the system is designed to ignore them, because if it reacted to every small fluctuation, it would be overwhelmed. It would generate false targets constantly. So the radar becomes selective. It learns to trust only what is strong and stable, and in doing so, it creates a blind spot. Anything that is weak and unstable is automatically treated as noise. Even if it is not, the bee too exploits that blind spot perfectly by ensuring that whatever energy returns from its surface is not only small, but also inconsistent. It does not present a clean, repeatable signal. It presents fragments, pieces that do not align over time, and without alignment, there is no confirmation. Without confirmation, there is no detection. This is why stealth is not about being invisible. It is about controlling probability. The probability that a signal will cross the detection threshold, the probability that it will remain stable long enough to be recognized, the probability that it will be interpreted correctly by the system. And if you can reduce those probabilities far enough, the object effectively disappears. Not physically, but statistically. And here's where the situation becomes even more complex. Because modern radar systems are not just passive receivers. They're constantly processing, filtering, comparing, trying to extract meaningful patterns from chaos. But that process itself introduces limitations, because the more aggressive the filtering, the more likely you are to remove weak but real signals. And the less aggressive the filtering, the more noise you allow in, increasing false alarm. So radar is always balancing between two risks: missing a real target or reacting to something that is not there. And there is no perfect solution. Every system has to choose a threshold, a line between signal and noise, and that line can be manipulated. The bee, too, does not need to overpower the radar. It only needs to position itself on the wrong side of that line, just below the level where the system is willing to act. And once it is there, it becomes extremely difficult to detect. Not because it cannot be seen, but because it does not meet the criteria to be recognized. And this reveals the deeper truth. The battle is not about energy alone. It is about interpretation, about how systems decide what matters and what does not. And by shaping the signal in just the right way, the B, too, turns itself into something that the radar chooses to ignore. So the real battlefield is not the sky. It is the threshold inside the radar, the invisible boundary between signal and noise. And the B, too, is designed to live exactly at that boundary, where detection becomes uncertain, and uncertainty becomes invisibility. Now, even if a radar manages to detect something, even if a weak signal rises just enough above the noise to trigger attention, the story is still far from over, because in modern warfare, detection alone is almost useless. Seeing something for a brief moment does not give you control over it. It does not allow you to engage it. And this is where another misunderstanding appears. People think that once an aircraft is detected, it can be targeted, but in reality, there are several layers between detection and interception. And each layer requires a higher level of certainty. The first step is detection. A signal crosses the threshold, and the system says something might be there. But that is only the beginning. The next step is tracking. And tracking is a completely different problem. It requires continuity. The system must receive consistent data over time. It must observe how the object moves, how its position changes, how its velocity evolves. And from that information, it builds a trajectory, a prediction of where the object will be in the next moment. If the signal is weak, unstable, or intermittent, this process becomes extremely difficult because the system cannot confidently link one detection to the next. It cannot tell if the signal it sees now is the same object it saw a moment ago, or just another random fluctuation. And without that continuity, tracking fails. And without tracking, the next step becomes impossible. Targeting, because modern weapons do not chase where the object is. They chase where it will be. A missile needs a continuous stream of updates. It needs a stable track to guide it through space, to adjust its path in real time, to converge on the target. And if that stream is broken, even briefly, the guidance solution collapses. This is where the B, too, gains a massive advantage, not by avoiding detection entirely, but by making detection unreliable, by ensuring that any signal it produces is not strong enough or stable enough to support tracking. It turns every detection into a question mark. Something that appears, disappears, shifts unpredictably, never forming a clean, continuous path that a system can follow. So even if a radar operator sees something on the screen, even if for a moment there is a hint of a target, that is not enough, because the system still cannot act. It cannot generate a firing solution. It cannot guide a missile. It cannot commit resources based on uncertainty. And here's the critical point. Modern air defense systems are designed to avoid false engagements. They cannot afford to launch missiles at every weak signal, because that would waste resources, expose position, and potentially create more problems than it solves. So they rely on confirmation, on multiple consistent detections, on stable tracking before they act. The B, too, exploits this requirement perfectly. It operates in a space where it may be noticed, but never confirmed, where it may trigger suspicion, but never reach the level of certainty required for engagement. And that difference between suspicion and confirmation is everything. Because in that gap, time is created, time in which the aircraft can move, approach, complete its mission, and leave, while the defense system is still trying to decide whether what it saw was real. This is why detection is not enough, because detection without confidence does not translate into action. It does not create control. It only creates doubt. And doubt is something that systems are specifically designed to eliminate before they respond. So the bee, too, does not need to be invisible at every moment. It only needs to break the chain between detection, tracking, and targeting. It only needs to disrupt the flow of information that turns a signal into a threat. And once that chain is broken, the entire defense system is reduced to observation without influence. It can see fragments. It can suspect. It can question, but it cannot act effectively. So the real advantage of stealth is not that it prevents detection entirely, but that it prevents detection from becoming something useful. It turns information into uncertainty, and uncertainty into hesitation. And in a system that depends on precise, continuous data, even a small disruption is enough to make the entire process fail. Once detection becomes unreliable and tracking begins to break, the problem shifts into something deeper, something less obvious. Because track-go is not just about following a signal. It is about predicting motion. And prediction requires confidence. It requires a stable stream of information that allows the system to project the future based on the past. Every tracking system works by taking discrete measurements, small snapshots of position and velocity, and connecting them into a continuous path. And from that path, it estimates where the object will be next. Not where it is now, but where it is going. Because by the time a missile reacts, the target has already moved. So everything depends on this prediction being accurate. But prediction is fragile. It depends entirely on the quality of the data. If the measurements are strong and consistent, the system can build a reliable model. It can reduce uncertainty. It can narrow down the possible future positions of the target. But if the data is weak, intermittent, or noisy, that model begins to collapse. The uncertainty grows, and the prediction spreads out into a wide range of possibilities. Instead of a precise point in space, the system now has a cloud, an expanding region where the target might be. And the larger that region becomes, the less useful the information is. Because a missile cannot chase a cloud. It needs a point, a specific solution to converge on. This is where the B, 2, operates with extreme effectiveness. Because it does not just reduce the strength of the signal, it disrupts the continuity of the data. It creates gaps, inconsistencies, small variations that prevent the system from forming a stable track. And without that stability, every prediction becomes less certain. Imagine trying to follow a moving object in the dark, but you only see it occasionally. A brief glimpse here, another glimpse there, each one slightly different, slightly delayed. And in between those moments, there is nothing, just emptiness. You can try to guess where it is going, but your guesses become less accurate with each missing piece of information. That is exactly what happens inside a radar tracking system when dealing with something like the bee. R. The data points do not align cleanly. They do not form a smooth trajectory. They form fragments scattered in time and space. And the system is forced to interpolate to fill in the gaps, to assume continuity where there may be none. And every assumption introduces error, small at first, but growing over time, because errors do not cancel out. They accumulate, they propagate through the system, expanding the uncertainty with each step of the prediction process. So instead of narrowing down the target's position, the system begins to lose it. The predicted path becomes less precise. The future position becomes less certain. And eventually, the uncertainty becomes so large that the prediction is no longer useful for engagement. This is why tracking is not a passive process. It is an active computation, a constant attempt to impose order on incomplete data. And when the data is deliberately degraded, when it is designed to be just unreliable enough, that computation becomes unstable. The B, 2, does not need to outrun the radar. It does not need to overpower it. It only needs to introduce enough uncertainty into the tracking process that the predictions lose their value. And once that happens, the entire engagement chain begins to fail, because a missile guided by uncertain data is not just less accurate, it is fundamentally ineffective. It may head in the general direction, but without precise updates, it cannot adjust correctly. It cannot converge. It cannot guarantee interception. So the system hesitates again, not because it cannot detect, not because it cannot track at all, but because it cannot trust the prediction. And without trust, there is no action. Because acting on bad predictions can be worse than not acting at all. And this reveals another layer of the strategy. Stealth is not just about hiding in the present. It is about corrupting the future. It is about making every prediction unreliable, every estimate questionable, every trajectory uncertain. So the real weakness is not in the radar hardware. It is in the mathematical process that turns data into prediction. And by controlling the quality of the data, the B, 2, controls the outcome of that process. And once prediction fails, tracking becomes meaningless. And when tracking becomes meaningless, interception is no longer a problem of physics. It becomes a problem of uncertainty. And uncertainty is exactly where the B2 is designed to win. By the time you reach this point, it becomes clear that the real advantage of the B2 is not a single feature, not a single trick. And this is where the idea of the $2 billion secret begins to make sense. Because what you are looking at is not just an aircraft. It is a system designed from the ground up to control how it interacts with energy, information, and uncertainty. When people hear that the B2 costs around $2 billion, they imagine that the money is spent on size, on engines, on payload, on something visible. But that is not where most of the complexity lies. The true cost is hidden in decisions that are not obvious. Decisions about shape, materials, alignment, thermal behavior, electromagnetic behavior, and how all of these elements work together as a single coherent system. Start with the shape. The flying wing is not just an aesthetic choice. It removes vertical surfaces that would otherwise act as strong reflectors. It smooths transitions. It eliminates sharp discontinuities. And more importantly, it ensures that most incoming radar energy is redirected away from the source, not by accident, but by design. Every angle is calculated to avoid sending energy back. But shape alone cannot solve everything, because no geometry can eliminate reflections entirely. And this is where materials come in. The surface of the aircraft is engineered to absorb part of the incoming energy, reducing the strength of what remains. And even more importantly, altering its characteristics so that the return signal becomes less coherent, less recognizable, less useful to the radar system. Then there is alignment, something that seems almost trivial, but is actually critical. Edges, panels, and structural features are carefully arranged so that their reflections do not reinforce each other. Because if multiple surfaces reflect energy in the same direction, they can create a stronger combined signal. And the B. 2 avoids this by controlling how those surfaces interact, breaking up any potential reinforcement. And beyond radar, there are other signatures that must be managed. Heat, for example. Engines produce enormous amounts of thermal energy, and that energy can be detected by infrared systems. So the B2 is designed to reduce and diffuse its heat signature, spreading it over a larger area, mixing it with the surrounding air, lowering the contrast between the aircraft and its environment. Even the way air flows over the aircraft is part of the design, because turbulence, exhaust patterns, and pressure differences can all create detectable effects. And controlling those effects requires a deep integration of aerodynamics and stealth, not as separate disciplines, but as a single unified problem. So what you are really paying for is not invisibility. You are paying for the ability to control interactions at multiple levels. Electromagnetic, thermal, aerodynamic, informational, all working together to reduce the clarity of the aircraft's presence. And this integration is what makes it so expensive, because it cannot be added later. It has to be built into the system from the very beginning. Every component, every surface, every joint must be considered in terms of how it affects the overall signature. And even small imperfections can create detectable returns. So the level of precision required is extremely high. Maintenance becomes part of the cost as well, because the materials and coatings that enable this behavior are not simple. They degrade over time. They require constant attention, careful application, precise repair, and all of that adds to the complexity, because stealth is not a one-time achievement. It is something that must be continuously preserved. So the $2 billion is not just the price of building the aircraft. It is the price of designing, integrating, and maintaining a system that operates at the edge of what is physically and technologically possible. A system that does not try to dominate through force, but through subtlety, through control, through the manipulation of information. And when all of these elements come together, shape, materials, alignment, heat management, precision, they create something that is not truly invisible, but functionally elusive. Something that exists in the environment, but refuses to become a clear, reliable signal. So the real secret is not hidden in a single component. It is hidden in the integration of many small decisions, each one reducing certainty just a little more, each one pushing the aircraft further into that space where detection becomes difficult, tracking becomes unreliable, and prediction becomes uncertain. And that is what you are really paying for. Not invisibility, but the engineering of uncertainty at a level so precise that even advanced systems struggle to turn what they receive into something they can act on By now it might seem like the B. 2 is the entire story. Like everything depends on how the aircraft is designed. But there is another side to this, something just as important. Because no matter how advanced a radar system becomes, it is still bound by a fundamental limitation. It must decide what is real and what is not. And that decision is where its greatest weakness exists. Every radar is constantly receiving information, far more than it can ever fully interpret. Signals from the ground, from the sky, from objects large and small, reflections overlapping, interfering, shifting in ways that are not always predictable, and to function at all. The system must filter this flood of data. It must choose what to keep and what to ignore. This filtering is not optional. It is necessary, because without it, the radar would be overwhelmed. It would see everything and understand nothing. So it applies thresholds, patterns, expectations, rules that define what counts as a valid target. And anything that does not meet those criteria is discarded. Not because it does not exist, but because it does not fit the model. And this is where the hidden weakness appears. Because the radar is not just limited by physics. It is limited by its own interpretation of physics, by the assumptions it uses to separate signal from noise. And those assumptions can be exploited. The more sensitive a radar becomes, the more signals it receives. But that does not necessarily make it more effective, because increased sensitivity also means increased noise, more background, more irrelevant data that must be processed and filtered out. And this creates a paradox. To detect smaller targets, you need higher sensitivity. But higher sensitivity makes it harder to distinguish those targets from everything else. So the system is forced into a balance. If it sets the threshold too high, it misses weak signals. If it sets it too low, it becomes overwhelmed with false detections. And there is no perfect setting, only trade-offs, only decisions about what kind of errors are acceptable. The B. 2 is designed to live exactly inside that trade-off. Not strong enough to be clearly detected, not weak enough to be completely absent, but positioned in that uncertain region where the radar cannot easily classify it, where every return is ambiguous, where the system hesitates between accepting and rejecting the signal. And hesitation is not just a human problem. It exists in the algorithms themselves, in the way data is processed over time, because modern radar systems rely on pattern recognition, on consistency, on the ability to confirm that what they are seeing now matches what they saw before. And when that consistency is broken, the system struggles to maintain confidence. So even as technology improves, even as radars become more powerful, more sophisticated, more capable of detecting faint signals, they do not escape this limitation. They only move the boundary. They push the threshold slightly lower. But the fundamental problem remains. They still have to decide. And that decision is always uncertain when the signal is engineered to be ambiguous. This is why stealth is not a problem that can be completely solved by building better radar, because the limitation is not just in detection capability. It is in interpretation, in the need to distinguish meaningful information from meaningless noise. And that need cannot be eliminated. It is built into the very nature of sensing systems. So the B, 2 does not defeat radar by being beyond its reach. It defeats radar by operating within its limits, by understanding how those limits arise and positioning itself where those limits are most restrictive, where the system is forced to question its own data. And this leads to the final realization The conflict is not between aircraft and radar. It is between certainty and uncertainty, between a system that needs clear answers and an object designed to avoid providing them. The B, too, does not disappear from the physical world. It does not break the laws of physics. It simply ensures that the information available to the radar is never complete enough, never stable enough, never convincing enough to produce a definitive conclusion. So the hidden weakness of radar is not that it cannot detect signals. It is that it cannot escape the need to interpret them. And when interpretation becomes uncertain, when the line between signal and noise is blurred, even the most advanced system begins to struggle. And in that struggle, in that narrow space between detection and certainty, the B, too finds its advantage, not by hiding, but by making sure that what is seen can never be fully trusted.